Oh, wow, I'm sorry. Now I feel even worse. Well, kudos to you. At least you guys don't have one then, like at 3 o'clock. That stinks. Well, let's get to it. Maybe I'll finish early. Okay. Well, first, that's what I was going to ask. Any questions about stuff? Anything keeping you up late at night? All right. Of course, I realize not all the classes here, but they did send me the reports, of the evaluations. And the bottom line is what you're wondering is, no, I'm sorry, the majority of the class was apathetic, I guess. Disinterested, lazy, I don't know why, but there was only 60-some% of you between the two that decided to fill it out. Those of you that did, though, thank you very much. I have them all here. But what that means is I can't give everybody extra credit. It is anonymous, so those of you that did fill it out, I don't even know who you were, so I can't give you credit, but that's the point of anonymous. But some things I've learned, I thought I'd explain a few things and comment on some others. Let's see. I highlighted some. Having more help with homework and tests by having homework and review sessions with the student teacher outside the classroom. That's a great point, and I wish I could. I didn't design this class, the structure of it. We meet Monday, Wednesday, Friday. There's no recitation. They don't block out any other times associated with this. I would love to have a lab with this class so you guys could be hands-on with some of this stuff. They did not design it that way. I keep giving them comments and suggestions, but I'm not the one that gets to decide that. However, we do have a teaching assistant that I know is extremely underutilized by the majority of the class because she says she hardly sees anybody. But she's there for you. A lot of people have contacted me and come in for extra stuff. But yeah, a regular appointed one, I agree, that would be ideal. But this class doesn't have such a thing. Maybe spend a little more time with the concepts behind the demonstrations. In general, people love the demonstrations. Good, because I do too. Thank you. I think they help a lot. As you notice, I use them to teach the concepts. Or we've covered a concept to reinforce it. But I admit maybe I could make the connection better each time I do demos. I intend to, but maybe it's not coming across as well. So I'm going to work on that. Call me on it too. I think you realize I really want this to be an open, informal, comfortable setting where we can have fun together, learn together, make mistakes. So yeah, if you got a question or like, whoa, 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 I don't get that. Call me on it. I love that the course is available on YouTube. This really helps with reviewing for exams. Oh, great. Good, that was my intent. Mostly to help you be able to review. Because I know you can't get it all the first pass. Which is one reason I encourage you to read the text. Either you get it first from me, and then when you read the text, hopefully it makes more sense. More ideally, but more difficult, is read the text first. At least have an idea of what's going on there. So when I explain it, oh yeah, okay, and I'm here to ask questions. But my idea with there, you get 2 passes. But with a video, you get a 3rd. That's good. Thank you. This one. I feel the professor does a great job of giving every opportunity to understand the material. Thank you. Good. There were several comments, too, that more people than not seemed to enjoy that there were lots of tests. I realize I give you more tests in this course than probably normal courses. And I explained that before. My rationale is, well, then each test is worth less. So there's less pressure, because some people just spaz on tests. Also, the units kind of lend themselves to that. We study these concepts, and before we go off on something different, or before I try to cram even more info and you have to remember it for the whole half the semester. That way you can get it over with before you forget about it. That was my intent. There are a few that don't like that many tests, but more people seem to like them than not. Oh, international student, this was aspects they wish were changed. International student can use the dictionary in the test. You can. So if you've been hindered because you don't understand my vocabulary, some of you have approached me, but if you're still, you don't understand the English, I'm not trying to test you on the English, the physics, so you could have asked. I'm sorry, but yes, I'll let you use the dictionary. As long as you're not slipping notes in there and cheating. But I'll trust you until you break my confidence. So let's see. I like the homework being due every week. I like that we have lots of tests. It would be nice to have the course integrated onto Canvas. I agree with that one, and I'm working at that. Canvas cannot do online homework yet. That's why I'm using WebAssign. And I chose to, instead of sending you to both, I was just doing it all on WebAssign, trying to make your lives easier so you didn't have to go back and forth. However, I know Canvas is trying to talk with WebAssign so that I could do everything else in Canvas and through there send you to WebAssign, take your grade, and the grades would go back into Canvas. But right now they don't have an integration for that. That's why I've just kept it in WebAssign. But they're working on it. I like Canvas better myself. Okay, I like this one. Sorry if you're in the room, but I don't like having the homework due on a Sunday night. For some reason, it's a little more difficult to remember, but also if it were due during the week, the student would be more inclined to look at it before Saturday and Sunday, so they could ask questions about the homework during the class periods. Good point. If you are waiting to Saturday before you ever look at it, then yeah, that's a good point. My intent was, I figured, I could have it due Friday when we're done, but I might as well give you a couple extra days. I was trying to help. True, it might be harder to remember things on the weekend, but it's due Sunday. That doesn't mean you can't do it earlier. And if you are waiting till Saturday to look at it, change your study habit. You should look at it from the get-go. Not necessarily answer it and turn it in, but know the questions so that when you read the text and come to class, a lot of the answers are just given to you. And then you know where you're confused and you can ask the questions before it's too late on the weekend. That was good. So thank you very much. Thank you. I just wish more of you had, so I'd get even more feedback. Comments? All right, while we're on logistics, and before I forget, enjoy your spring break next week. We will finish the material, yeah, I should, today for chapter 15 and 16. But so I don't give you the test right when you come back, we'll review. And any questions you have or concerns on Monday after spring break. But then I'll test you on it that Wednesday. Because this is heat and thermodynamic stuff. Next will be chapter 19, which was, is that waves? I forget what it calls it, but it has to do with sound. Vibrations and waves. So we'll move on to a different. Also, friendly reminder, I know you want to play on spring break, but after spring break you will only have 2 weeks before your superhero paper's due. So if you want to get, you haven't, and you want to get a head start, it's due no later than April 1st. The instructions are online. I require a printout as well as a digital copy. Everything that I'm going to grade you on's in there. Read it carefully. Reread it so that you don't miss points because you didn't see what I wanted. Okay. Got that. Got that. Oh yeah. There was a couple other comments too about they wish there were more problems to work or better reviews. So I want to remind or bring to your attention that I can still see who looks at the keys to all the homeworks and the exams, And relatively few of you are actually looking at the keys, thus seeing what the correct answers are and my explanations that explain why it's that way. So you're not taking advantage of that. I know some of you are, but the majority obviously isn't. Same with the exams. My explanations are there. The clicker questions I give, they're all from the same bank. They're the same style. The homework is what I'd like you to know. There's checkpoint questions in the book, and there's hundreds of questions at the end of each chapter to practice. If you didn't realize yet, the odd answers are all in the back of the book. So there's ample questions to check yourself or to practice on. And if you find one that I don't specifically cover and you're confused, bring it up. I'm sure somebody else is confused. Well, we'll work on it together. Okay, good. So last time we did conduction, convection, and radiation. 3 ways of heat transfer. Heat is like work. Remember, it's a change form. And the way it can move and change is conduction, convection, and radiation. That's how this internal energy, heat, can flow and go from one thing to another, the different types. We ended with radiation, and I want to show the types of radiation it can look like. So let me pull the screen down. So you have a better feel of what this electromagnetic radiation looks like. It'll come in handy because when we study waves and vibrations, those are waves, sound waves, and then we're going to study light, which is electromagnetic radiation, a wave. And so I'm going to expose you to it now. This is what a wave looks like, specifically an electromagnetic wave. I thought I had it looping, sorry. Guess you have to do it again. There we go. So we haven't studied electricity and magnetism, but there's an electric field and a magnetic field. You can think of the yellow as one and the blue as the other. And they're oscillating. At any given point, like you can watch the Y, it increases and then decreases back down. It's fluctuating there. The magnetic field the electric field becomes stronger this way and then more negative this way, and then back to 0 and positive, 0 and negative. And the magnetic field's doing a similar thing, the blue. But they're in different directions. That's what an electromagnetic wave is. An oscillating electric and magnetic field. But they form a sine wave. They're oscillating, they're changing. You can represent it with a sine wave. The distance between these peaks, from this yellow peak to that peak, is a wavelength. It's that distance. Same with the blue, it'd be the same distance from one peak to the other. And so it's oscillating up and down at a certain frequency, a certain rate, how fast it goes up and down. Like with sound, doo, versus ooh. That one's lower. It has a longer wavelength down here with a longer wavelength, and it's vibrating more slowly. It has a lower frequency. It sounds silly, but people remember it if you do it like that. And higher frequencies are vibrating faster and sound higher. Shorter wavelengths. And sound like Mickey Mouse. Did I hit it? Nope. Here we are. Here's the electromagnetic spectrum. You've probably heard of these. Radio waves, TV, radar, microwaves would be in here. Infrared. Visible light is really skinny. Doesn't take up a big portion. Ultraviolet, X-rays, gamma rays. That's the known electromagnetic spectrum. They all look like the picture we just showed. But they vary in wavelength, frequency, and energy. Gamma rays have the most energy. increasing energy this way, which means they are oscillating very quickly, have a high frequency, in really short wavelengths. Where the other end, radio waves, are much longer and bigger and vibrate more slowly and have less energy. And how that relates to us is radiation, form of heat transfer, is related to temperature. Remember, average translational kinetic energy. And they're oscillating. The electrons change orbitals and give off energy in the form of an electromagnetic wave. And the hotter it is, which way do you think it's shifted on the spectrum? Left or right? To the left. Hotter objects have more energy and are oscillating faster. The peak frequency emitted off of something that's really hot is higher, and vice versa. So, in the visible range, something that's hot enough to glow so that we can see it, to give you an idea, that's pretty hot, like charcoal or a candle. It's burning so that we can see it. So most things like us at room temperature, well, we're not. We're a little above. But the tabletop, it's cooler. It doesn't emit visible light of its own. But it does emit light that we can't see. Electromagnetic waves. It emits some infrared. And if it's even cooler, it might emit radio waves. The sun's really hot, so it emits visible light, but it also emits ultraviolet and some X-rays because it's got even more energy. But everything emits. The peak frequency that you see of light is proportional to its temperature, how fast those molecules are moving around. Yes, Brian? Microwaves are relatively longer. Yes, they're in the radio wave range. Yes.
Okay, so then a microwave oven, how is that working? Is it misnomer? Is it mislabeled?
No, a microwave oven emits microwave radiation, which is in the radio waves. So, dim that back up. Over there on the right. They are, relatively speaking, longer waves. But they have enough energy to cook our food. You can remember microwaves like that because,
surrounded by, like with Wi-Fi, those are waves?
Yes, we're surrounded by electromagnetic radiation everywhere. The lights emit visible light. We emit infrared. The sun emits ultraviolet. We get that. The earth emits radio. Radios emit radio. TV. Cell phones, microwaves. Wi-Fi, generally in the microwave region. They're everywhere right now, through us, in us, around us.
So a lot of people get cancer, and is that just radiation?
General radiation of the stuff I just mentioned, normal exposure, doesn't cause cancer. But if you get too many X-rays, that increased energy in an X-ray doesn't agree with tissues, and it can kill tissue and create cancer, sure. That's why we shield ourselves or limit it. People that fly a lot, when you get higher in the atmosphere, you're less shielded from cosmic rays, gamma rays, high energy rays. They get exposed, pilots can get exposed to more radiation. You have to fly a lot to maybe make that a factor. But you don't want to stand right in front of your microwave door, because if it leaks, you're getting exposed to high energy microwaves that start heating up your tissue. That's not good. That's actually how they discovered the microwave. The basic story goes, someone was inspecting an installation, and they were running microwaves, really big industrial machinery. And afterwards, he realized that his chocolate candy bar in his pocket had melted. He put 2 and 2 together and, long story short, realized, hey, we can cook food with this. It heats it up. These can represent water molecules. And what that does is the electrons, the water molecule themselves, the atoms with the electrons, absorb the microwaves, that energy, which gives these more energy, right? Energy is conserved. And so they start vibrating. And if they vibrate, what do? They bump into their neighbors and start making them move and increase their kinetic energy. And if they start to translate, their temperature increases. And that's what the water molecules do. The microwaves get absorbed. It has more energy, starts vibrating, knocking its friends around, increasing their temperature, and cooks your food. It's clever. But if you don't have water content, something doesn't have water, you can't cook it in a microwave. Metal just reflects the microwaves. It never absorbs them, so it doesn't get hot. But you can make nice sparks and things with electric fields and whatnot. So that's radiation. That's what we're talking about. Let me pass these glasses out. Then we'll borrow this class. Take one, pass it around, and once they're passed out, we'll do that demo. Meanwhile, I'll show you a different demo. This is an infrared camera. Excuse me. A thermal imaging camera. So it's detecting infrared radiation from your bodies. Let me dim the lights a little more, but not so much you trip. It doesn't need visible light. That's not what it's detecting. See, it looks the same. It's picking up the infrared radiation, electromagnetic waves. And if something is hotter, it shows up as brighter on there. So we can see his face is nice and warm. Good for you. But his jacket is absorbing some of that radiation, and so it doesn't get through to the camera. Let's pick someone else here. Let's see. See if we can notice any anomalies. I don't know. Hair is generally cooler. Oh, look, he's looking through the glasses. You can see because his eyes look darker. Here's somebody with glasses. The glasses absorb the infrared radiation, so they look cooler to the camera. Literally. Okay. You can wave and see. The person waving up there, you got a hat on, I assume? Can't see it. Yes. It's kind of fun. Let's try over here. Let's see. I wonder, can I see the camera back there? Let's look at the camera. Oh yeah, look at that on the on the tripod. The camera is a little warmer, and so you can see it's a little hotter. The laptop is warm as it's dissipating in heat. Let's shine it over here on this door. See if I can find it. We'll see. Oh, good. So here I am. Hi, class. Oh, look, my fingers must be colder. That's poor blood circulation, I guess. I don't know. But this is all to emphasize, again, we emit infrared radiation, and hotter objects emit more energetic energy. The temperature is proportional to the frequency, vice versa. If I rub my hands together, they should get hotter, right? Friction. Let's see if we can tell a difference. Can't really tell with my fingers, but if I touch the door, in theory, my hand is warmer than the door. And heat flows from hotter objects to colder objects. So my hand cooled and the door warmed up, and you can see my thermal handprint. Thank you very much. You can use it to draw things. Let's see here. Yay! But that's what they're doing with thermal imaging. That's why you can see at night. You don't need the visible. We'll just do something different. Let's look at the projector and see if it does anything fun. Nope. Nope. Higher. There it is. Hello. There. It's pretty warm up there. Anyway, you can inspect your home this way and see where any heat is leaking, transferring outside. It's kind of fun. Okay, bright light. Now, let's turn that off. I want you guys to see some of this effect. With your glasses, look at this light bulb. And it'll be more effective with the lights out again, of course. Those glasses are diffraction gratings. And we'll discuss what's going on later, but it's splitting the light up into its constituent colors, the colors that make it up. So you should see a rainbow, right? Hey, I don't know if this would work, but it's worth a shot if he wants to play around. The camera guy can hold this over the front of the camera, and maybe the light will get diffracted into it. Who knows? So, you see red, green, and blue. Is that correct? Those are the three colors that make up white light that our eyes respond to. This is nice and hot, so it's hot enough to emit light, visible light. If I dim it, watch the light bulb. Tell me what colors change. Observations, comments? Good, red and green. The blue should have gotten dimmer. Can you see that? Less blue, more blue. Less blue, more blue. Can you see that? Give me some confirmation.
Well, when you reduce the wavelengths on the light bulb, can we turn on the lights? I can't see them.
Oh, details.
Okay, when the light bulb is bright, that means that the wavelengths are shorter. And when the light is dimmer, that means that the wavelengths are longer. Is that right?
Nearly. Nearly. When the bulb is brighter, it's hotter. So it emits red, green, and blue. And blue has more energy, shorter waves. So there are shorter waves, but it's still emitting the red and the green. All those temperatures are there. When it's cooler and thus looks dimmer, you just see the red and the green, the longer waves. The short blue waves disappear because it's not hot enough to emit those. And you can gauge the temperature of a fire or stars that way. That's how astronomers know how hot a star is. A red giant star is cooler than a blue giant because blue has more energy. And a white dwarf is white. So that's emitting all of them, red, green, and blue. It's even hotter. That's how you can gauge it. It's kind of fun. All right, I'll pass this back around so you can throw them back in. Did you get one? So, question.
Kind of like having it's like the RGB in a computer. You know, it saturates each RGB so that it shows white on the screen. So that's an interesting parallel, an interesting comparison between stars and the red, green, and blue.
Yeah, the red, green, and blue. The red, green, and blue make up the pixels on a television screen or a computer monitor. And we will discuss, I hope to discuss that more when we get to light and color. That's my favorite topic in physics. But good observation. So question for you. If everything is emitting radiation because it has a temperature, why don't we just run out? Why doesn't everything just give up all its energy, cool off, and we all die of a cold death? Consuming. So, and that's my point. Not only does it irradiate, but it's constantly absorbing too. And there's a net effect. If you have a blob of something, the energy does not change. Well, let's put it this way. If it's absorbing energy, then its temperature goes up. It can. But if it's giving off energy too, like we just said it was, and they're the same, then it's absorbing and emitting, radiating at the same time, and so its temperature stays constant. But if you put more in than you get out, what will this thing do? Exactly. The temperature will increase. That we call a net absorber. A net absorber, because it's absorbing more than it radiates or emits. And vice versa. What if it gives off more than it absorbs? The temperature goes down, and we call it a net radiator or a net emitter. This is all explained really well in your text too. Some good examples. So let's do black versus white. On a summer day, a hot summer day, would you rather wear black clothes or white clothes? Why? Yeah, so you know this. We say black is a good absorber. And this has to, you can remember this with visible light. When you see something black, that means no light is reflecting off of it for you to see. It's absorbing all the colors. So it looks black to you. It's a good absorber. Well, it's true in the whole range of the electromagnetic spectrum. Infrared. It absorbs it. Thus it gets warm. Its temperature increases. White tends to reflect. If all the colors are bouncing off, even it doesn't absorb infrared as well either. It reflects. And so it's not a net absorber. Well, it can be. Eventually, white can heat up. But it takes longer. We say white's a poor absorber. Black's a good absorber. A harder question. Let's say you're out all day in black and your friend's in white. All day, though. You've had a chance to get up to the same temperature. Now it's nighttime. Who's going to stay warmer longer? The one in black or the one in white? Have you ever thought about that one? Everybody knows that black seems to heat up faster, but does it cool down faster, or is that white?
Well, it's already absorbed some energy from earlier in the day, so it's warmer wearing the black.
You would get warmer faster wearing black. But eventually, let's say black and white get to the same temperature. Now you're going to cool off. They're going to be net emitters. Who will cool off faster? Things that are good absorbers are also good emitters. So black will cool down faster. And you can use that to your advantage. So something that's white, if it starts out as the same temperature as something black, black will give up that energy and transfer it away quicker and cool off, changes temperature faster than something white. What if something that... No, I think I got that a question. I'll save that. Hold on. These, there's examples in your book, so you'll know the answer if you read. They're called blackbody boxes. They talk about black bodies as an ideal example. And the idea here is the temperature of this box and its insides are at equilibrium with the room. It's all the same temperature. The inside of this one's the same temperature as this one. When you look in that hole, what color does it look, the hole? Black. And same with this one. Well, this is what's inside. It doesn't matter what color is inside. They're the same temperature. So they emit the same waves. And so the temperature color looks the same. If we were to heat up both of them and they got to where they emitted visible light, then we would start seeing it glow. But if they were the same temperature, we'd see the same color glowness. Glowness, is that a word? And I even like that this one, even though it's white inside, I put different materials here, duct tape, some black paper, and a piece of rubber. But which black circle, the one I put or the hole, looks darker to you? Good. Most people think the hole does. That's because these are absorbing visible light, but not as well as the hole. If light goes into the box, it bounces around and gets absorbed by the walls in here. And so there's less of it to reflect back out. And so it's a better absorber than these different pigments. The container itself. Your eye is an example. Your pupil, it looks black. That's not because the inside of your eye is black. It's just because light goes in, gets absorbed, and nothing comes back out. Unless you flash a person. If you put enough light in, then it flashes off your retina, and it looks red, which is the color of your retina. Infrared thermometers. Review, I mentioned that that's how they take temperature. They're just picking up the infrared. And let's turn this one on. The greenhouse effect applies to this. See, they're at about the same temperature, room temperature, roughly. I have a thermometer inside a box with a clear lid. And this one that's open to the room. They read the same temperature. Any radiation from this lamp, visible, infrared, ultraviolet, go into the box and get absorbed by the walls of the box. The box isn't as hot as the light. So does it emit longer or shorter waves? Cooler objects will emit longer waves. Well, longer waves can't get through the plastic. It's like short waves can get in. The plastic is transparent to shorter waves, but it's opaque and blocks longer waves. So now that when this starts to warm up, it radiates, but those can't escape, and it heats up even more inside. That's called the greenhouse effect. It's like on a hot summer day, leaving your pooch in the car. Bad idea. Seriously, it can get really hot. You can see already that the box is getting hotter. And greenhouse gases, you've heard of global warming? That's the idea. greenhouse gases like water vapor, which is natural, and carbon dioxide, short waves from the sun, because it's hotter, can get in. But they heat up the earth and us and buildings and cars. And we emit longer wave radiation because we're not as hot. And that gets reflected or absorbed back in, stays here. It can't escape back through. It's a greenhouse effect. And that's what keeps us warm. But if you block too much because you have excess carbon dioxide, it might get too hot. And that's what they're worried about, global warming. Are we going to get too hot because we're creating too many greenhouse gases, and we're trapping this heat? To be determined.
What happens if it gets too hot?
Well, lots of things. If it gets too hot, more ice melts, which then displaces the oceans and changes its height and depth, which can affect land on the shore. Maybe they get flooded. Maybe the more ice is floating. Things can shift. That can change the ecosystem and the biosphere in different places, which can encourage some species to grow and others to die, which then affects others because of the food chain. There's a cascade effect. In general, they think if we warm up too much, it's bad. Does that make sense? And you can see, that's long enough, 34, 26. And this will retain the heat longer too, because it still can't escape. I'll turn it off in a moment. Let's do one more. This is called a fire syringe. And one I was thinking I didn't explain as well as I would have liked was that bicycle pump and the 2-liter bottle last time. We made a cloud in the bottle. What I wanted to try to emphasize or show that worked, but I don't think I made the connection well, is that when I did work, I exerted energy and pumped air into the bottle. So I'm doing work, energy goes in. Where does it go? In doing work on the air in there. And we stored energy potentially. But it makes the air, shoves more and more in, and they're running into each other. The air actually warms up. And so my work energy got converted to heat in there. This is similar. This is flash paper, a little piece of cotton paper that I'm going to put in this syringe and seal it off. And it's basically a piston. When I quickly compress the air, I'm doing work on the system. The air heats up, pushing the molecules together, and they don't like that. And if you heat it up enough above the flash point of the paper, it will ignite. Let's try it. Dim the lights slightly. Watch down here at the base. Are you ready? 1, 2, boom. And just like a car piston, after it heats up, that makes it expand, and I can actually feel this thing getting pushed back up into my hand. You can start fires this way. Another scouting thing I've learned. There's a birch tree out here. If you take the bark, it's paper thin. Due to time, I'll spare you. It doesn't look as cool anyway. But you can put a little piece in there, and it works. You can compress it, and it'll ignite. The reverse is true. When the pressure was so great, it blew the cork. Pressure was released. It now did work on the environment. And when the air left, the pressure drops, the air expands, and it cools. And that's true in our environment. When air goes up, there's less pressure on it. It expands and cools. Becomes more dense and sinks. If it's near something hot, it expands, becomes less dense and rises. And that started our convection. That's what happens when the air comes over to our mountains. When it goes up, forced up the mountain, it's cooled. That's why it snows up there. Because as it's forced up into less pressure, it expands and cools. And things condense out of it. And you can go skiing. All right. 5 minutes. I didn't end early, but now I'll give you a few clicker questions. So you guys can have credit for staying, all right? I'll turn this light off and we can observe. This is 45 degrees Celsius, that one's 30. So definitely a greenhouse effect happened. We'll see who cools off faster too. Oh yeah, one more thing I didn't cover. Read about Newton's law of cooling. Newton's law of cooling. Basically all it means is, we've discussed it, the greater the change in temperature, the faster something changes. There's a brilliant law. But that means if you want something to cool down, stick it in the refrigerator where it's colder. There's a bigger change in temperature, so it'll change faster. That's all Newton's law of cooling means. So when you read about that, that's what I want you to know. The larger the change in temperature difference between the two things, the faster it'll change its temperature. Duh. Okay. Oh, enter your password incorrectly. There we go. Did it go back to computer? Let's log into ResponseWare so you guys can have a session ID number. There it is in the bottom right. Session ID number. Raise your hand if you still need the session ID number. Okay. We can ask you a couple questions here. Did you get it, Tal? All right. Polling is now open. If you hold one end of a metal bar against a piece of ice, your hand will eventually become cold. Does cold flow from the ice to your hand? A piece of metal, touch some ice. Does cold flow to your hand? I want to see what your gut is, so I'll start counting. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, 40% of you are still thinking yes. The answer is no. Which way does heat flow? Hot to cold, period. But that's in the normal world, we like to think that. Oh, that's cold, and I'm starting to feel cold, so cold must have flowed. What was really happening? Heat was leaving you from the hotter to the colder, making you feel colder because your temperature's dropping. So it's always hot to cold. Hot to cold. Okay? Think about this one. It's not meant to be a trick. Warm air rises, that mountaintop thing that we were just talking about. But the valleys stay relatively warm and green. Why? Polling's open. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, more of you thought C. Good, because it's A and B. So most of you realize, as we just discussed specifically, when warm air rises, there's less pressure, it expands, it cools. That's true. So it's colder up there. But something else is going on. There's more air down here. And remember the three methods of heat transfer? Conduction, convection, and radiation. The best way to keep something the same temperature? Put a lid on it. Like an insulating lid of air. And what's that do? It keeps any of these particles from conducting away to the higher particles. It's blocking. It's also stopping convection flow because it can't go above. And anything that's warm, like the ground and the car, emits, and maybe some of it's getting trapped, the radiation. So putting a lid on something is the simplest way to keep something at the same temperature, whether it's warm or cold, because heat transfer is hindered. So that's going on also. Well, I'm out of time. So we can review more, of course, Monday. So have fun.